Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in this particular video we're going to be looking at how to determine the total number of electrons given any specific quantum number. And before we actually dive into this, please don't forget to hit the like so that others can actually get the chance to check out this video, and also subscribe, because of course subscribing is free. So let's dive into this by looking at a particular question, and our goal here is to be able to associate a question to various theories that you know, and how that's going to be brought back to this particular question in order for you to solve effectively. So looking at this particular question here, you're asked to determine the total number of electrons, and the total number of electrons could actually be held in a sub-level. So there are a couple of things to keep in mind here. One is total number of electrons that could be held in a sub-level with an angular momentum to be equal to 3. So looking at the plan here, the plan is to be able to actually start first from angular momentum, and from the angular momentum we're going to go all the way to the total number of electrons in a specific sub shell. And so the angular momentum, and we're going to look at a specific sub shell that will actually lead us to how many electrons are found in that subshell. So subshell, there are a couple of things to keep in mind on which subshell or what are the things that is specific to this particular question. And now for you to actually go about this, we're going to look at the theory behind all this stuff that we actually are talking about. And the theory we're going to be looking at is, hey, of course we're dealing with quantum numbers here, because we are looking at how sublevels is actually truly linked, and alongside the angular momentum are both linked to quantum numbers. So in here we're going to look at the 4 quantum numbers again in total, and from the 4 quantum numbers, this is going to actually lead really well into which quantum number is actually important enough for we to determine the total number of electrons. So 1, which is the first quantum number, in this case is actually represented as n, which is in this case is called the principal quantum number. And this actually tells us the energy levels that are actually present in an atom. And so the next one here is actually represented as L. This is actually called the angular momentum quantum number, and this actually is associated with the specific shape of our specific orbitals. And next here is actually looking at the m subscript L, which actually is highly linked to the magnetic quantum number, and the magnetic quantum number is actually highly explaining the specific orientation of our specific shape. So in a specific shape, you might have other orientations within that specific sub-level or subshells that are important enough for you to analyze how the electrons, which leads to our final particular quantum number, is the spin quantum number, which actually explains how electrons are positioned in those orientations that we are actually going to be looking at. So looking at this, we are actually linking, based on our question, the angular momentum to our specific total number of electrons. And angular momentum highly links really well to our subshells, because angular momentum explains the subshells that are present in an energy level. So looking at this particular energy level here, we have energy levels going from 1 to any number. There must be integers, and in this case there also must be positive integers. And in here we have n equals 1 all the way to n equals 2, and then we have n equals 3, and we have n equals 4. Let's just stop at 4 for now. We can go on and on, but you know what, we're going to go from 1 to 4. That is really easy and straightforward. And so moving on to the next part here is how do you associate the angular momentum to the principal quantum number? And in this particular case here, we associate it using our specific formula, which is L is equal to n minus 1, where in this case here, where n is equal to 1, L is equal to 1 minus 1, which is equal to 0, and it tells us the shape, which means that it is spherical. So we have a spherical shape. That's a bad spelling for sphere. I also spell it as S-H, no, not S-H, S-P. So spherical, eraser. A spherical, and that is a sphere for that particular orbital. And the next one here is when n is equal to 2, what is L? So in this case, 2 minus 1 is equal to 1, and this actually introduces our p orbital, which are lobe-like in terms of the shape. And then the next one here is when L equals 3, we have 3 minus 1, which in this case is 2, and 2 represents our d orbitals. And then finally here, when n is equal to 4, our L is 4 minus 1 is equal to 3. So looking at this, we know that 3 is actually represented as f orbitals. And so when you're looking at this, you're like, there's something interesting here. We know that the question says what? Angular momentum equals to 3. And we know that angular momentum, based on this particular theory, is actually represented as what? Solution. When angular momentum is equal to 3, we know that angular momentum is equal as well to L. So therefore, based on our theory and our understanding, we notice that, hey, this satisfies the question that is actually given, which in this case here, when n equals 4, L equals 3. Therefore, in this particular case, we can actually link our L equals 3 to the total number of electrons in that particular sub-level, which in this case, our sub-level is actually F. So when the sub-level is, in this case, F, we are going to count how many, like the total number of electrons that are in the, or that can fill up our f orbital. And in this case here, to go about it, we need to notice or determine what is the formula. And the formula is pretty much generic when this is actually applied in this particular question. We know that based on our analysis, by analyzing, I would say, the specific total number of electrons in a specific sublevel is actually equal to 4L plus 2. And based on this, we can then put our specific L to be equal to 3 in that particular equation. And therefore, our total number of electrons in our specific F sublevel or subshell is equal to 4 times 3 plus 2, which is equal to 14 electrons, as the total number of electrons that will be in our angular momentum equal to 3, which in this case is equal to L. So this is a fantastic way to actually determine what our answer is for that particular question. And there is another method to go around this. One other method is by linking or by confirming through your ML and your MS. And our MS is actually known as the magnetic spin. And we know that ML, in this particular case, which tells us your orientation going down, in terms of how you represent it with our L's, we actually know that this L is actually an integer that are present from negative L to 0 and to positive L. So therefore, applying it to this particular example here, which in this case L is equal to 3, it means that we're going to start from negative 3. The next integer going from right to left on the number line is actually negative 2, negative 1, 0, 1, 2, 3. So in total here, we have how many sub-levels or orientations in that sub-level? Sorry, how many orientations do we have in our sub-level? We have 7 orientations, and for each of these orientations, which in this case is 7, we must have 2 electrons that must be present in each of the orientations. That has to be obeyed using our spin or our Pauli exclusion principle, where in this particular case here, you must have 2 electrons that must fill each orientation in the sub-level. And in order for you to do that, these 2 electrons has to be incorporated here. And once you have that taken care of, we can then actually determine how many electrons will be placed in here in our for we to determine our total number of electrons as you move from one orientation in the same sub-level all the way to the other specific orientation in the same sub-level. So when you address this in terms of 1, knowing that 2 electrons, which I'm going to write here, first is that 2 electrons, they must be in each orientation. And the next one here that we need to consider is that, hey, we do have, in this case, 7 orientations. I'll just put orientations in the angular momentum, which in this case is where L equals 3. Therefore, we can actually put them all at the same energies because they are all having the same shape, or they are all coming from the same shape, which means that if you are coming from the same shape or the same sub-level, your energies will be equal, and so each orientation will have the same energy or equal energy. So in here we have 1, 2, 3, 4, 5, 6, 7, and then following our Pauli exclusion principle and the Hod's rule, we are going to fill them up with electrons. So therefore, we're going to start off by putting 1 electron on each particular orientation. In this case, we have 7 electrons, and then we pair it up with an opposite spin, which in this case will give us in total 2 maximum electrons in each orientation, and in total here we're going to have 14 electrons. So this way is also a great way to check that this is actually the right answer to your question. So that's about it for this particular long video. I hope you're able to understand the 2 ways by which you can go about solving this particular question, involving you being able to identify the total number of electrons in a specific sub-level, in this case when the angular momentum is given, which is in this case 3. You need to create a plan, and from the plan, look back to your theory. Remember what are the ways to go about it. Remember, most importantly, the key formula to keep in mind, which is 4L plus 2 for our specific sub-level total number of electrons. And this will be the great key that will be important enough for you to determine how many electrons are present in that specific sub-level. And if you want to determine it using another method, which is combining our ML with our MS, which in this case is the spin quantum number, maximum number of electrons in each orientation must be 2, opposite spin paired, and this particular case will be able to fill them up in the specific orientations, and as a result of that, we'll be able to determine our final answer right here. So Thanks for following me through this. Truly appreciate it. Please hit the comment down below. Let me hear your thought about this particular example and other suggestions on better way to actually approach these particular questions so that everyone can actually benefit from this. All the same, stay smart. Please don't forget to hit the like, share and subscribe. Of course, subscribing is free. By that way, I can see you all soon. Stay smart and believe in yourselves.